In this video, we're going to do a harder example that'll involve concepts like supply and demand and surplus and shortage. So here's the example. When a vendor, actually let me preface this. What might make this a harder example is the fact that it's a word problem first off, and there are multiple steps to this. Okay, so here's the example. When a vendor sells a bag of chips for $2, it sells 5,000 bags. Decreasing the price by $1 leads to 1,000 more sold bags. Let Q of P be the linear demand function in thousands of bags. So when I say in thousands of bags, that means Q, the value of Q, will be in thousands. Okay, and then it says, and let Q of P equal square root of P plus 1 plus 2 be the supply function. So remember, we call the demand Q, and we also call the supply function Q. And I've mentioned before that it's going to be clear from the context which is which. So this problem tells me specifically which one the supply function is. It tells me the supply function is this one. So we don't want to mix that up and think this is the demand. It tells me this is the supply function. Okay, and then it asks, how much should the vendor charge to not have a surplus or a shortage? How many bags will it sell at that price? Okay. So with this problem, pause the video for about 4 to 5 minutes. 4 to 5 minutes, and really try this question on your own. This is going to be really, really good practice. So 4, 3, 2, 1, pause the video. Pause the video for about 4 to 5 minutes and try this. All right, so hopefully you've done that. If not, I really encourage you to pause the video and actually try this. Getting that practice now is going to help when it comes to tackling questions similar to this on the homework and on quizzes and exams, because you'll already have gone through the process of thinking about it at least one time before you even get to the homework or get to the quiz or exam. All right, so how do we begin? So we have this question. So in terms of what the question is asking, it's saying we don't want to have a surplus or a shortage. So we don't want a surplus or a shortage. So no surplus or shortage means we are talking about equilibrium. That's what no surplus and no shortage means. So that means we want supply to be equal to demand. Okay, and we have an equation for the supply, but we don't for the demand. So let's find an equation for the demand. That is a good place to start. So let's find a demand equation. Okay, so for the demand, let's use the info that it gives us to convert that into some points. So the first piece of information that it tells us is when the price is 2, remember P is the first coordinate, and the other coordinate is going to be Q. Q is going to represent my demand. And it tells us that when the price is 2, it sells 5,000 bags. But I don't just put 5,000 here. And that's because the question says that this linear demand function is already, the units are going to be in thousands of bags. So Q should be in thousands. Which means instead of writing 5,000 here, I get to just write 5. And that means that the actual quantity that we're talking about is 5,000. Sorry, 5,000. All right, and then the question tells me an extra bit of information that I use to get an additional point. It says that when we decrease the price by $1, so that would make the new price $1, that leads to 1,000 more bags being sold. So 1,000 more bags. So plus 1,000 bags when we do this. And this is minus $1 in terms of price. So when we add 1,000 bags, that means the quantity is going to be 6,000, so I write 6 for Q. So this is my Q value, that's my P value. Okay, so I have 2 points. Let's get the slope. So the slope is going to be 6 minus 5 over 1 minus 2. So that's 1 over negative 1, which is negative 1. So that's our slope. And at this point, we are ready to write down the equation because we have a point, we have 2 points, and we have a slope. So we write, using point slope, y minus the y coordinate, and I could choose either one. Maybe I'll choose the second point. Y minus 6 equals the slope, -1, times x minus the x coordinate, which was 1. And of course, in my problem, we don't have the variables y and x technically. We have q and p. So y is actually q, and x is actually p. So we have q minus 6 equals -1 times p minus 1. And if we rearrange this and isolate the q, so if we distribute the -1, we'll get negative p, we'll get +1, and then adding the 6 over, we'll get +7. Okay, so this right here is our demand function. All right, so we got the demand function, and we've said before that we wanted to find when there is no surplus and no shortage. And we said that, well, that's equilibrium. So let's just recap that. No shortage or surplus means that we are talking about equilibrium. And that's really the key to determine what sort of direction we're going to take to solve this. Okay, so I want to find when equilibrium happens, which means now let's set the demand equal to the supply. So we got the demand, it's -p + 7, and the supply, so looking back up to what the supply equation, so the supply is q equals the square root of p + 1 + 2. So let's copy that down. Okay, so the supply is square root of p + 1 + 2. All right, so now we have an equation that has a square root in it. So this is sort of a practice problem from algebra. At this point, if you didn't get this far before when you paused the video for 2 minutes and see if you can solve this equation from here. So 4, 3, 2, 1, pause the video. Pause the video and try to solve this for about 2 minutes. So that may not be enough time to finish solving it, but I mostly want you to think about how you'd get started and what the key ideas are. All right, so hopefully you've done that. Hopefully you've paused the video for about 2 minutes to think about this. Now let's talk about it together. So if I have an equation with a root, what we first want to do is we want to isolate that root. We want to get the root by itself. So let's isolate the root. And to isolate the root, let's move this +2 to the left. So I'll get -p + 5 equals the square root of p + 1. And now let's square both sides to get rid of the root. So I get -p + 5 equals root p + 1, but let's square both sides. So let's square this side, let's square this side, because that's going to get rid of the root. So if we do -p + 5 squared, -p + 5 squared means -p + 5 times -p + 5. And then if we FOIL this out, we'll get p squared, we'll get -10p, and plus 25. So that's what we got on the left. We get p squared minus 10p plus 25. On the right, when you square this square root, it'll cancel the square root and we get p plus 1. All right, so now we have this quadratic equation. But to handle this, let's move everything to one side so the other side equals 0. So I'll move the p plus 1 to the left. So that'll give us p squared minus 11p, 25 and minus 1, that's plus 24, equals 0. And now that it's equal to 0, I can go ahead and try to factor this. And if I do that, actually, let me just scooch this up so that we don't get distracted by that. So we get p, and then p, what goes in these parentheses? It's minus 3 and minus 8. Okay, so p could be from the first parentheses, 3, or from the second parentheses, it could be 8. So we get two possible values for what p could be. So there is something really important that we need to be careful about when we have these equations with even roots. So in an equation with an even root like this one, we need to check for, so this is a bit of algebra review, what do we check for if we have an equation with an even root when we solve it? We check for what are called extraneous solutions. And what extraneous solutions are all about is when you have an equation like this that you're solving, sometimes we can end up with answers that don't actually work when we plug them back in. And there are a few scenarios where that type of thing can happen. One is when there's an equation that has variables inside of even roots. Another situation is if you have variables with inside of absolute values. There are a few others, but this is definitely one where we need to check for extraneous solutions. Okay, so why is that? Why do we need to check for extraneous solutions when we have even roots? I want to discuss why, because one of our key course goals is really to master the content that we talk about. So I don't want you to just know that, oh, this is a thing that I do. Like when I have an equation with an even root, I check for extraneous solutions. Like it's good to know that, but to really master the content, we need to understand, wait, why? Why do we check for extraneous solutions? Why can I end up with answers like this that might not work when I plug them back in? Okay, so here's the answer. And the answer is when we solve an equation like this. For example, I had a square root in my problem. Squaring both sides removes what's called a restriction. It removes a restriction in my equation. And what I mean by that is when I have the square root of some stuff in my equation, the square root of some stuff is not allowed to be certain types of numbers. When I take the square root of something, it is not allowed to give me out a negative number. So when I square both sides, what happens? So let's look at an example. So if I have the square root of some stuff, and let's say that I say this is equal to -3. Well, that's clearly not right, so I'm going to put a sad face. The square root of some stuff can't be equal to a negative number. This is something that's just not true. Square root of some stuff is never going to be equal to -3. At least not when we're just working with real numbers. But let's look at what happens to this equation that's just not true when I square it. If I square this, the square root goes away and I get stuff. So maybe let me just say in parentheses, after squaring, what happens? Well, on the left-hand side, I get stuff. On the right-hand side, I get -3 squared. But -3 squared is a positive number, it's 9. And now I have that the stuff, whatever was inside the square root, is equal to 9. And that could be true. The stuff could be equal to 9. This could be true. So when we do this step of squaring both sides, it can take an equation that's not true and give me something that is true. But then when I work with this thing, this sort of lower equation, this one that could be true, if I were to plug that back in to this original equation, the one where the square root of stuff equals this negative number, it's not going to work. Because nothing works in this equation where the square root of the stuff equals this negative number. And the reason that happened is when we squared both sides, that removed this restriction. It removed the restriction that the square root of some stuff can't be a negative number. So you might think back to what you've learned like in algebra class before, in terms of solving equations. Whatever we do to one side of an equation, we do to the other side of the equation. But it turns out not every single operation works just fine. There are some operations that we do to both sides that we have to be careful about. And squaring both sides of an equation to get rid of a square root is one of those instances where we have to be careful. That's why we check for extraneous solutions. Okay. All right, so we've talked enough about this, I think. So let's go ahead and actually check for extraneous solutions now. All right, so I've gone ahead and just given myself a little bit more room here. I've copied down the equation again, and we want to check for extraneous solutions. So I've just abbreviated the word extraneous. And we had these two answers that we got, p equals 3 and p equals 8. Let's plug them both in. Okay, so if we plug in 3 into the left, we get negative 3 plus 7. Plugging it into the right, we get square root of 3 plus 1 plus 2. I'm going to put a question mark over the equal sign. That's typically what I like to do when I check for extraneous solutions, because I don't necessarily know that these are going to be the same. So negative 3 plus 7, that's 4. On the right-hand side, square root of 4 is 2. 2 plus 2 is 4. At this point, I do know that they're equal, so I can get rid of that question mark. So 4 equals 4. Okay, so we're happy with this. I'll put a check mark, I'll put a smiley face. P equals 3 works. If I plug in 8, I get negative 8 plus 7 equals square root of 8 plus 1 plus 2. At this point, maybe you already see that it's not going to work. The left-hand side is negative 1. The right-hand side, square root of 9 is 3. And 3 plus 2, that's 5. Oh, I forgot to put my question mark up here. Okay, I needed to put a question mark because I wasn't sure that they were going to be the same. But after I simplify them, I know that they are definitely not the same. Negative 1 is not equal to 5. Okay, so that did not work. So when there's an answer like this that does not work, what I do is I like to put a slash through it, and then I like to say that this is extraneous. And I'll just abbreviate that again as EXTR. So anytime we have answers and we need to check for extraneous solutions, if an answer is extraneous, I need to indicate that. So it's really important that I actually write that 8 is extraneous, like I've done. Okay. So what this means now is, well, we have our p-value, the price. So that's $3. The units are dollars. Remember, this is how much a bag of chips sort of needed to cost for us to be at equilibrium. That was one part, I believe, of what the question was asking for. It wanted to know how much, so the first part of the question was, how much should the vendor charge? In other words, what should the price be to not have a surplus or shortage, to be at equilibrium? So we just found that price. That price is $3. And there's one more part to the question, which is how many bags will it sell at that price? So how many bags are actually going to be sold? In other words, what's the quantity that's sold at this price? So if we want the number of bags, we want the quantity, which means we want Q. But do we want the Q from the demand or the Q from the supply? Because in general, those are two different Qs. So we need to plug in, and we can plug into either, actually. We can plug into the demand or the supply in this specific instance. Since we found equilibrium, this was the equilibrium price. That's what the $3 was. And both the demand and the supply are equal at equilibrium. So we can plug into either because $3 is the equilibrium price. All right, so I get to pick. I get to pick whether I want to plug into the demand or if I want to plug into the supply. So let's look back to our demand and our supply to see which one looks simpler. So our demand was this, negative p plus 7. That looks pretty simple. Let's just do a quick check. Supply was the square root function. That's still not going to be terrible by any means. It's still going to be pretty simple. But I think demand looks especially simple, so let's plug into that. All right, so let's go ahead and plug into the demand. Okay, so if I plug into the demand, in other words, into Q equals negative p plus 7. So if we go ahead and plug in $3, if I want to know what Q of 3 is, I'll get negative 3 plus 7, which is 4. Okay, so the Q value is 4, but remember what the units are. The units are important. And the units for Q were thousands of bags. So we were talking about 4,000 bags of chips. And that is our answer. So finally, returning to our goals from the beginning of the section, we've now defined supply and demand. We've learned how to write them as linear functions and find equilibrium, which is when the supply and the demand are the same.